Alright, welcome to this series where we're covering Unreal Engine's character movement component in depth. So in this video we're going to be making wall running, and this is going to be fully multiplayer compatible, network safe and everything like it always is. And it's going to feature a wall run and then a wall jump off of the wall. And if you're new to this series where we're covering the character movement component, it's going to be hard to jump right into this video because it's a lot more useful to have started from the beginning. But you can do it. I would say if you're already really comfortable with C++ and you've been doing your own custom character movement component stuff, then you're probably fine to just jump into this video and see how I do it. But if you are a bit finicky with C++ or you haven't really made your own custom character movement component, I would really recommend at least watching the first 3 videos in this series just to get it under your belt, to get everything set up, because we are going to be using code that we've previously written. We're going to be working on top of all that because by this point I think our character movement component is like over 1,000 lines of code, so it's just not worth rewriting all that for every video. That said, all of the code is in GitHub. In the description there's a link for that, and if you are following along with this video and you need any help or something doesn't work out, you can join a Discord because there's plenty of helpful people there that have already been helping each other out now, which is really exciting. Coming over the character movement component, previous tutorials, stuff like that. So yeah, so we'll be making the wall running, and the new things or the topics of this video are going to be a new movement mode. We're going to be working with saved move variables and the saved state. We're going to be doing a float curve, which is a new tool we're going to use to fine-tune movement a little bit more. And we are also going to be doing jump overriding, but unlike the previous video where we overrode the jump input, we are going to be overriding the jump execution. Alright, so as always, let's look at a high-level overview of what we're going to be doing. So here's our character capsule, and here's the wall that they're going to be jumping onto. So the idea is that the player will run up to this wall and jump up, and then when they're in the air, so only when they're in the falling movement mode, they will automatically just start running along the wall if they have the right conditions met. You could change it so that they have to press a button or some other state needs to be valid, but we're just going to make this one automatic. It won't really matter however you want to do it, but I think automatic is how most games do it. So just as long as they're in the falling movement mode. And some of those important conditions that need to be met are that they have to be above a certain distance from the ground. So you can't just start wall running at like say 0 height. That would just kind of look weird. You also have to have a certain amount of velocity along the surface of the wall. So if you're running into the wall, just like straight into the wall, you won't wall run. But if you're running kind of alongside the wall and you jump up, you will enter that wall run. And you also need to have a certain a limited amount of vertical velocity. So if you're falling like from a very high height, I decided to make it so you can't wall run because it's kind of immersion breaking, but maybe in your game, if you want to be able to be falling very quickly and still wall run, you could just not implement this condition. But yeah, those are the main conditions for entering the wall run. And obviously there needs to be a valid wall up against you. And then when you're in the wall run, that'll just be a custom movement mode that pretty much just moves you along the wall with a projected velocity that we'll go over. And there'll be a slight amount of gravity kind of pulling you down unless you keep against that wall. So I decided to make it so that when you let go of the controls, like when you let go of W, you will slowly start to fall down the wall until you exceed a certain Z velocity, and then you kind of just step off the wall. And then lastly, if you press spacebar or jump or whatever your jump input is while you're running on the wall, you will perform a wall jump. So you'll just kind of jump off the wall, and you'll have a boost in Z velocity. You'll also get kind of pushed off the wall, and you'll also maintain some of the velocity you had along the wall. So you kind of just jump off, and then you could use this to say jump onto a wall, like onto a corner. So if there was another wall, you could jump and ride that one, or you could just jump onto the ground or whatever. So yeah, let's get into the code. Alright, so here we are in the header file of our custom character movement component. And the first thing we're going to do is we are going to add a value to our custom movement mode enums. So by now you should have this custom movement mode enum, which contains all of your custom movement modes, and we're going to add wall running to that. If you don't have this, just create this and just make wall running the only entry for now. But if you did have the other movement modes, you can just add it in. And this is just to keep track of what movement mode we're in for the custom movement modes. All right, so the next thing we're going to do is we're going to come down to our transient, or I like to call them working variables, and we're going to add the state for wall running. And this will be a safe variable, so we'll need to make a saved variable for this. But importantly, so all I kept for state was the b wall run is right. And so this boolean just indicates whether the wall that you're running on is on the left or the right. And the reason why I kept this so simple, I was going to choose to do like a wall normal or something like that, but you always want to keep your safe movement variable state at the absolute minimum it can be. The goal is to just keep this as low as possible, because most of this state, unless you're talking about compressed flags, most of this state is not actually replicated from the server to the client. So like the idea is that the more state you have that isn't replicated, the more chances there are for a desync to happen from packet loss or something like that. So I'm just keeping this simple boolean, whether the wall is on the left or the right. And that's really all we need for the state. Because other than that, it's just whether you or not you are wall running, which is just the movement mode. So then let's add in the corresponding saved variable to our saved move. And so again, if you're not following along with this series, I would definitely recommend watching like my third video where I cover like creating this saved move class, and you really need to understand what this is doing. But basically, we need to make a saved variable which will cache the value of our safe variable for when we have to do net corrections. And this will make it so that our state is completely synced up between the server and the client. It's not actually replicated, but it's just that if the server ever issued a update, the client will be able to replay the state in the exact way the server did, given that the state before was in sync. So yeah, basically this is just a variable corresponding to that variable. Next, we're going to drop in all of our parameters. So for the wall run, there's a decent amount of parameters here. We have the min wall run speed, which is that minimum speed that the player has to be moving to run against the wall. We have the max wall run speed, which is the max speed they can move while on the wall. The max vertical wall run speed is basically, I use this in two ways. I use this to clamp the vertical speed and also to threshold or to condition the negative vertical speed. You'll see how we use this later. The wall run pull away angle. This is a weird thing I added because it just was intuitive. I think it's in other games, and so I figured I should add this. Is basically when you accelerate or when you use the WASD input or joystick input or whatever, and you pull away from the wall, you'll sort of quickly come out of the wall run, because oftentimes it's just intuitive to just pull away from the wall, and that's how you can exit wall run without like doing a wall jump or anything. The wall attraction force, this just pulls the player always towards the wall. And the reason I add this force is that, say you wanted to go around like a curved wall, or maybe you just or maybe because when we start the wall run you actually aren't right up against the wall, this force will just pull you into that wall always. The min wall run height is that minimum height that you have to be off the ground, measured from the bottom of the capsule, in order to start the wall run. So the reason I do this is just because it looks weird if you start the wall run at like 2 centimeters tall or something like that. It just it looks like you're basically walking, but just with a thin gap between your feet and the wall. So I add this threshold for the height. Wall run gravity scale curve. So this is going to be where we use the curve float, and this is going to tell us how much vertical gravity to apply based on sort of a combination of our input and our velocity vector. And then lastly, we have the wall jump off force, and this is just the horizontal force that gets added to the capsule when you do a wall jump. All right, so for the implementation, it's going to be pretty standard like always. We're going to have try wall run and fizz wall run. So pretty standard. We have this way to get into the wall run, and this function to update the wall run over every frame. Now we need to override some default character movement component functions, and those are going to be public functions. Those are going to be can attempt jump and do jump. So this is going to be how we get that wall jump. We need to make sure that we override the way that the player can jump and say they can also jump in a wall run. And we need to override the do jump to add our little horizontal force if the player is doing a wall jump. And then lastly, we'll make some just helpful getters down here under the interface. These will just tell us if we're wall running and if the wall running wall is on the right. And I use these, I think, a couple times in the character movement component, but also I make them blueprint pure so that I can use them in the animation blueprint. All right, so let's jump into the C++ file now. And we'll start with just making that state variable, that safe movement variable, movement safe by throwing it into all the saved move functions. So first, for can combine with, we're going to add this little entry. So if the wall running is right value changes between this move and the new move, we don't want to combine these moves. And then for clear, this is also pretty simple. We're just going to set the wall running is right to 0 just to clear that value if we want to reuse a saved move struct. So set move 4 is also pretty standard, just storing the value from the character movement component into our saved move value. And then prep move is the exact opposite. We are putting the value from the saved movement class into the safe value in the character movement component. All right, so since we did make a new movement mode, we are going to do a little bit of bookkeeping because we implemented some other functions in the past that we're also going to need. So the first thing is get max speed here. This is one of those things that you do need to just update for every custom movement mode. So we're going to add an entry here. So if we're in wall running, we're going to return the max wall run speed, which is this parameter we made. And this is not trivial, obviously. This will tell you how fast the character can run on the wall. And then we also need to do get max braking deceleration. And that's pretty simple. We're just going to do 0. We're not going to do braking on the wall. We're going to let the fall off or sort of the gravity handle that situation. So there's not going to be any manual braking. So we're also going to add in here can attempt jump. And this is going to just check whether we're allowed to jump or not. And so the super of this obviously doesn't know that we made the movement mode while running. So it's just going to do stuff like check if we're moving on ground or if we're falling, and if we don't want to crouch, stuff like that. But we actually also want to add the fact that we could be wall running and jump. So we're going to say if any of the previous super values was true, and those conditions were met, like say we're just walking on the ground, we can jump. Or also if we're wall running, we can also jump. And then for the do jump, so this is going to be similar. So we're going to first store a variable that says was wall running, and we're going to get the is wall running value from that. And then we're going to call the super do jump. And the super doesn't actually just straight away do the jump. The super actually checks first if it can do the jump. It actually at some point down the line, it actually calls this function, and it will return true if it did the jump and false if it didn't. And so we actually want the super to run because it's going to do stuff like it's going to add some stuff to the z velocity, and it's going to set the movement mode to falling. And that's what we want, but we just also want to add a little bit of tangential force, a little bit of horizontal force to push them away from the wall. And so we are going to say if the jump was valid, if we did jump, then we're going to check if we were wall running. And so the reason we cached this value is because after we do the jump, we'll be in falling. So no matter whether we were walking or wall running, we will just now be in falling. So we need to make sure we saved what we previously were doing. So if we're previously wall running, then we're just going to do some casts here. And this is going to figure out whether the wall run was on the left or the right, but specifically it's going to get the wall normal. So we're going to say we're just going to say start is equal to the component location, and the cast delta, it's kind of a weird way to do this, but so the cast delta is equal to the right vector times the capsule radius times 2. So just this short little distance out of the capsule and then the end is just going to be equal to start plus cast delta or start minus cast delta, depending on whether the wall run is right. So hopefully this kind of makes sense to you. Basically, we're saying if the wall run is right, then cast a ray out to the right of the player, and if the wall is on the left, cast a ray out to the left. And that just depends on whether we do plus or minus cast delta, because it's the right vector. And then we're making this params, and this is going to be our query params, and this is going to be the value of character owner, zippy character owner, get ignore character params. And so if you've seen in previous videos, this function I made is just a nice helper function I make in all my projects, where I basically just make a collision query params, and I add the character and all its child actors and components and whatnot, and then just get this value. And what's nice about this is that I just can put this in all my code and not worry about ignoring the right actors, because for most of the time we don't want to include the character in our geometry tests. All right, so then we're gonna get the wall hit, and we're gonna cast that, and we're gonna assume that this just hits because like we were previously wall running, so this is pretty much a guaranteed hit. We don't need to like check whether it hit or not. And then we're going to take that wall hit normal, and we're going to times that by the wall jump off force, which is that parameter we made, and we're just going to add that to velocity. So this is basically just, this whole thing is just adding a little bit of velocity that's just away from the wall. And that will make it so that we kind of jump, it looks more realistic, like we're pushing off the wall for the jump, instead of just jumping straight up, because that wouldn't really make sense on a wall. And then regardless, if the super did return true, we still want to make sure we return true, because this do jump is going to be, the value of this is going to be used by other stuff, so we still return true. And then if do jump was false, if the super was false, we return false. Alright, so now that the jump stuff is finished, we want to go to update character state before movement, and we're going to add our hook into wall running. So we'll come down to the bottom here, and basically, if you notice the pattern, whenever I do anything in update character state before movement, it's usually like a conditional check into some sort of mechanic, like a movement mode or a feature, so any mechanic like sprinting or wall running or sliding or proning. I kind of check and enter that mechanic in update character state before movement, because it makes the most sense, because you want to check all those conditions before you start the movement frame, so that you can be in the proper state. So anyway, these are, like you can see, like these are all just like, this is a hook into dashing, this is a hook into mantling, and this will be transitioning, and then this will be how we get into wall running. So basically we're just going to say if we are falling, then try wall run, just because you can't wall run other than if you're falling. So let's proceed on. So we're going to go to Phys custom. So remember, every time we make a new movement mode, we're going to need to do some more of this bookkeeping. So here's another good example where we have the switch case on our custom movement mode. And here's the most important one. This is the Phys custom. So this will be executed when you're in a custom movement mode. And we have to handle the situation where we are in the wall running movement mode. So just if we're in the wall running movement mode, then call Phys wall running and then break. And then lastly, before we get into the implementation, we're actually going to add one more thing to on movement mode changed. So what we're going to do here is we are going to handle the simulated proxy case. So like I said, like you want to keep the state to an absolute minimum, right? In that safe move variables. And the reason for that, one of the reasons, is because especially if this state affects things like animation, then you might have to replicate that, which is going to be a pain, because maybe you're sending over vectors and stuff like that to every proxy, which is obviously inefficient. So instead, what I decided to do was just keep it to a Boolean. But actually, we don't even need to send this Boolean to simulated proxies. We can actually just calculate it, because the simulated proxies will already get the custom movement mode replicated to them. So they will get this on movement mode changed. They will get this event triggered, because the custom movement mode is already replicated. It's a replicated variable. So when they get this trigger, we'll just do basically this similar check where we just cast a vector to the right, and we see, did that value hit? So we're gonna make this param. We're just gonna cast to the right, and we're going to perform this cast. And remember, this returns a Boolean whether we hit anything or not. And we're basically just going to say if we hit something, then the wall is on the right, and if we didn't, we're just going to assume it's on the left. And this is perfect for just like a kind of cheap and efficient way to detect whether the wall's on the left or the right when we start a wall run on the simulated proxies. And the reason this is important is because we're going to use the value of this in the animation blueprint to just make sure like kind of which side we're playing the animation on, because obviously the character kind of needs to hug the wall at a certain angle. So yeah, we're just going to be making this variable to check that. All right, so now let's finally get into the implementation of the wall run. So we'll come down and make a new section for the wall run, and I just pasted in try wall run. So I'll go through this. So first, we're just going to do all our condition checks, right? So the style, if you've been following along, you'll know the style I do these basically is I just do check after check after check, making sure all the conditions are met. And then once they're met, I just have a small little blurb that kind of starts that movement mode or starts that mechanic. So now let's go over these. So first, just if we are not falling, then return false. This is kind of a redundant check, but sometimes I bulletproof my code like this just in case, I don't know, maybe somehow someone else wanted to call this. So anyway, I don't know. Just if we're not falling, return false. If the velocity dot size squared 2D is less than min wall run speed, return false. So what this is doing is this is checking if our horizontal velocity is less than the min wall run speed. That 2D means basically the XY components of velocity. It has nothing to do with the Z component. So we're checking this because we need to have a minimum amount of velocity along the wall in that horizontal plane in order to enter the wall run. And if that's not even met, then we return false. And then if the velocity.z, so if that vertical velocity is less than negative max vertical wall run speed, return false. So this makes sure that we're not just falling very fast, because if we're falling extremely fast, even if we do have like a significant amount of horizontal velocity, I decided this just doesn't make sense to enter a wall run because it kind of seems unrealistic that you can fall extremely fast and be moving down and then instantly enter like a horizontal velocity. If you don't want that, if you think that'd be a cool mechanic to have, you can just remove this line basically. So now we're going to do the detection to check whether the wall is on the left or the right, or if there even is a wall there at all. So similar to what we had before, we're just going to say start is just the component location, and the left end is start minus this right vector times radius times 2, and right is start plus, so just on the left or the right. We're getting the param again, and we're making 2 hit results. One is a floor hit, one is a wall hit. So first we'll just check the player height, and we're just going to cast a line trace directly down, and the distance of that down is going to be the cap height plus min wall run height. So this makes it so that we're casting from the floor, from the bottom of the capsule to, down by some min wall run height. And if that cast hits something, we return false immediately. This just makes it so that we have to be a certain height above the ground in order to even consider wall running. Next, we're going to do the left cast. So we're just going to cast from start to left end. So just checking that left side if there's a wall on the left side of the player. And if there is a valid wall hit and the velocity dot the wall hit normal is less than 0, then we are going to, this is kind of like success condition. So what do I mean by this line? What this condition is saying is that the velocity has to be pointing kind of at the wall, or basically just not away from the wall. It's in the half space that is negative to the wall normal. And I just check this because if basically the reason I do this condition check is that when you perform a wall jump, you'll have a velocity that sticks you away from the wall. And if you don't have this check, then you'll immediately start to wall run again, because you'll still have enough tangential or horizontal velocity to wall run. So I need to do this check to make sure that you have to be moving kind of into the wall, or at least parallel with it, in order to enter the wall run. And so if this is met, then we technically are while running left because that was the left end. So we're going to set safe once to while run equal to false. And then for the right cast, we are going to just basically do the same thing but on the right side. So we're going to go from start to while end, and then we're going to make sure that condition is met. And if that's all good, we're going to say the safe while run is right is equal to true. And then if neither of those conditions, so this case only runs when neither of those were valid, we're just going to return false. So past this point, we can assume we have a valid while hit. So this value is valid, and also we have we had know whether the wall is on the right or the left. So we're going to get the projected velocity. So this velocity, this vector is going to be the velocity vector, but projected onto the plane of the wall. And then we're going to check if that size 2D is also less than the min run wall speed. And if that's the case, then we're just going to return false. So technically, you don't need this check because even if all this gets passed, we will run this check, and this check is more restrictive. So anything that passes this check will also certainly pass this check. The reason why I add this kind of seemingly redundant check is that if we can, eliminate a lot of frames where we're trying to wall run but we have not enough speed, we won't have to perform these kind of more expensive line traces. So, avoid line traces if you can when necessary, but this is a little bit of an optimization. You don't need to do this, but this will just cut out some of these line traces because, you don't even have enough speed to begin with, so why even bother? So anyway, if this is not met, we return false. And then after that, we finally say, okay, we've passed all conditions. So we have a valid wall, we're moving fast enough and in the right direction, and we can go ahead and enter the wall run. So the first thing we're going to do is just set the velocity equal to the projected velocity. So we're going to clamp that velocity so that we no longer can move like towards or away from the wall. We can only move kind of parallel with the wall. And then we're also going to set the z value of the velocity, so that vertical velocity, equal to the clamped value of the z velocity anywhere between 0 and max vertical wall run speed. So the reason why I'm clamping it like this is that if you're falling down and you enter the wall run, it makes sense to kind of start wall running straight, not wall running down. If you start wall running down, it's going to look like you're still kind of falling. It's just confusing the player. So we're going to kind of clamp that to be only greater than 0 and less than the max vertical wall run speed. That's just so that if you're wall running, like if you're somehow like shooting up very high and you have a lot of vertical speed, we want to kind of clamp that, and because it just will look weird on the wall. So after we modify the velocity, we go ahead and set the movement mode equal to move custom cmove wall run. So that's just entering the wall run movement mode. And here I just added a log function I was testing to indicate starting the wall run. If you watched the last video, we made these debug macros that helped us out, but you don't need to add this. This is just a nice thing so that when I enable debug mode, I can see when I start the wall run. And then since all those conditions are met, we're going to return true so that we can enter the wall run. And I made this a boolean for try wall run. It returns true and false, false when you don't enter and true when you do enter. But if you remember, I don't actually use that value. So here I just call try wall run. You don't have to make it a boolean, I guess. That's just the kind of the convention I do for all of these. So I just kept that convention, but you don't have to return a true or false because this doesn't even use it. But that's the convention, so that's why I kept it. Now let's move on to the actual physics of the wall run. Alright, so pretty meaty physics function, but nothing we can't handle. So, a lot of this is going to be boilerplate that you're going to just start getting familiar with. So first thing is just to do all our checks. So, if we don't have enough delta time, just get rid of it, return. And if we don't have a valid character or we don't have a valid controller or any of these other conditions are not met, we're also just going to return, get out of here. We're going to set just teleported to false because now that we're performing a move, we didn't just teleport. And we're going to set remaining time equal to delta time. So if you haven't watched any of the other videos, or you're just jumping into this one and maybe you didn't watch the ones where we make new movement modes, basically the way the phys movement mode works, the way that you write a phys function, is that, well, for one, this is what's actually going to perform the move, but we don't actually just perform it right away. We actually perform it in a while loop. And the reason we do that is because of this thing called substepping, which I cover in the prone video in more depth. But substepping is basically a way of iterating inside of the frame to get finer or more precise movement. And the reason for that is because the frame delta time is relatively large, but we have the performance usually to iterate over smaller ticks, and that'll just get the idea is that it just gets a higher resolution or a high accurate movement simulation. So we're going to make this value remaining time, and we're going to sort of eat away at remaining time and go through these substeps or these iterations in this while loop. So these are the big, you can read this whole thing out. While remaining time is greater than min tick time and iterations less than max simulator iterations, and yada yada, all these. This line, by the way, like some of this boilerplate code, I always just copy it from the default character movement component. And the reason for this is that they've sort of set up the standard or the convention of how to typically make a physics function. And yeah, actually I'll just show it real quick because it is pretty valuable. So I'll just go like the phys walking function. So you can see, they check the delta time, they check this boilerplate code, and here's their big while loop. And, they do similar stuff as us because this is kind of where I learned it from. And, we're trying to maintain that standard. So, after we do our checks, then we get into the while loop and we increment these iterations. And remember, this is important so that we don't perform too many iterations, because the idea is that, in a perfect world, your movement will work out fine, but in reality, you could potentially get in some loop where you iterate too often, you get into an infinite while loop. So we store the number of iterations just to make sure that we never do that. Again, setting teleported to false because now we're inside this tick, so we could teleport inside of the while loop. And we're getting tick time, which is kind of our new delta time. Tick time is like the working delta time of the while loop. And we're going to call the helper function get simulation time step. And that's going to eat away at that remaining time. Then we're going to subtract that from time tick. Then we're going to store the value of our old location. And then we're going to make a bunch of new parameters or new variables to help us with raycast and stuff. So, this looks very similar to before. We're going to make all these values for starting and the cast delta and the ending, and also the parameter. We're going to cache that. And we're also going to get this sine pull away angle. So here we're just going to convert our while run pull away angle parameter. First, we're going to convert it to radians, and then we're going to take the sine of that. And this is going to be the important useful value, but as a parameter, it'd be kind of weird and unintuitive to set this value. So we set the angle, and then we convert that to the sine of the radians of this angle. Then we're going to just make a hit result for our wall hit, and then we're going to cast that line trace and get that wall hit. And hopefully this is valid. The idea is that we're already along the wall, we already have a valid wall, and this will work out. But it could not be valid, like say we just go off the end of a wall. And then we're also going to make this wants to pull away. And this is going to be equal to if the wall hit was a valid hit and the acceleration is not 0, so the player is actively pressing or pulling the joystick in some direction or pressing WASD or anything like that. So if the acceleration is not 0 and the acceleration direction dot the wall hit normal is greater than the sine pull away angle. So that's just saying if you're pulling kind of away from the wall at a great enough direction, then we do want to pull away. So we're just going to check if the wall hit was somehow not valid, or we do want to pull away. Then we're going to get out of we're going to get out of wall running. So we're going to set the movement mode to falling. Then we're going to say start new physics on remaining time and iterations, and we're going to return. So the nice thing, the cool thing about this remaining time is that we could be, like say a third of the way through our while loop, stepping through this whole delta time that we're given, and then like somewhere in between we left the wall, and then we can go into falling, and then we can perform falling for the 2/3 remaining time of this single frame. So you can see we get that really good high fidelity simulation of movement with this sub-stepping approach. So then we're going to clamp the acceleration, because here we're going to start performing all of the acceleration and the velocity stuff. So we're going to say acceleration is just equal to the projection of acceleration onto the wall. And we're also going to remove any z acceleration so that you can't accelerate up or down the wall. And then we're going to apply acceleration. So we're going to call this calc velocity, and we're going to apply over a time tick, which is the simulation delta time, and zero friction. We're not in a fluid, and the max braking deceleration is, we already set that actually to 0, but yeah, that's going to just get that value. And that's just going to basically apply our acceleration to our velocity. So next, we're going to clamp a velocity to the wall normal. So we're going to project that velocity onto the wall and clamp that. And then we're also going to get this tangent accel value. So tangent accel basically says how much acceleration is tangent to the wall. And that's going to be equal to the acceleration dot get safe normal, and then dotted to the velocity dot get safe normal 2D. And that's going to basically say that if we're accelerating along the wall, then, if our input is along the wall, then this will be 1. And if our input is like 0, or if it's like in the opposite direction, this will be like -1 or 0 or whatever. So you'll see why we use this in a second. And then we're just also going to get this little boolean to check if the velocity is up. So if the z component of the velocity is greater than 0, then our velocity is up. So next, we're going to say that the velocity.z, we're going to add to that. So here's going to be our gravity. So the idea behind this is that when the player's running along the wall, if they like sort of let go of the input, or if they move backward against the input, they'll start kind of slowing down and falling down with this negative z velocity, kind of like as if like gravity is starting to catch up to them and they're running out of speed or something like that. So we're going to add on the get gravity z. So that's just going to get the z gravity sort of component that the character movement component uses in other parts, like in its walking and falling stuff. And then we're going to multiply that by this wall run gravity scale curve. So this is a float curve. So a float curve is a asset you make in the editor, and you define, it's basically just a graph. You define, points, x points corresponding to y points. And it's just really helpful. I use this a lot, actually, and I only thought to use it because someone in the Discord pointed out that they could use it for their thing, and I was talking about that, about like a floating mechanic. But I don't know why I didn't think about putting this in a tutorial before, because they're super useful, and they basically just allow you to define sort of a custom pattern or a custom curve, basically, of any sort of behavior you want. So the behavior we're making here is we're making a curve that converts z velocity, the tangential acceleration into z gravity scalar. So, so basically just the idea is that if you're pushing backward or not having any input, then you'll have sort of more gravity applied to you. But if you're pushing forward exactly with the character, like pushing directly into the wall, along the wall, then you'll have no gravity applied to you. So yeah, that's what this whole line is doing. And I'll show you what the curve looks like once we get into the editor, so that hopefully makes more sense. And then if the velocity size squared, 2D is less than min wall run speed, so that's that same check we did before. So if we start losing too much velocity, or if the z velocity is less than the negative max vertical wall run speed, which is again a check we did before, then we're also going to exit the wall run. So same thing here, just changing the movement mode and starting a new physics. Okay, so finally we got past all the velocity acceleration stuff and the checks to make sure we can still wall run. Now let's actually do the wall run. So we are going to make a delta, which is going to be velocity times the time tick, and then we're going to say 0 delta is equal to delta dot isn't equal to 0. So this is just going to check if we have any delta. If there's no delta, like why would we even bother performing the move, right? So if we have no delta, then just remaining time is equal to 0, and this will just accelerate that while loop just to end it so that we don't have to bother moving if there's no delta. Else, assuming there is delta, so like 99% of the time there will be some delta, then we're going to make a hit result hit, and then we're going to call this safe movement update component. So this is, if you haven't watched other videos, this is the single line that does all the movement. Well, there's 2 of them in this one, but this is kind of the big line. So this will actually move us by that delta, which is just our velocity times time, and like you see, that's like equivalent to like the basic kinematic dx equals vdt. And then we're just going to keep the rotation. We're not, so you'll see the character animated so that they're kind of an angle. We're not going to do that with the capsule. That's just kind of a waste of inefficiency, and opens you up to more network bugs. Usually you don't need to rotate the capsule. Like, I highly recommend not rotating the capsule. Just do that stuff with animation unless you really have to. So yeah, basically just keeping the rotation the same. We're going to sweep. So that means we're going to check the capsule movement, like from the whole, we're going to kind of sweep the capsule from the start position to the end position instead of just like kind of teleporting them. And we'll pass in our hit result. And then we're also going to move the character again by an amount that is kind of into the wall. So we're going to move them kind of at the wall. And this will just make it so that we're always keeping the character right up against the wall. We're not doing this through velocity because we want no component of velocity to be like into or out of the wall. We want all that velocity to be parallel with the wall. So we're just making this separate little force that's just going to push the character against the wall. Then we're just going to check if the updated component location is equal to O location. So if we didn't actually move anywhere, like we literally just staying stuck, then we're also going to say remaining time equals 0, and we're going to break. And this is equivalent to like if the delta, if the effective delta is 0. Because remember, the delta we made here, that is like our, sorry, where was that? Delta, which is like our idealistic distance we want to move. This might not be the actual distance because there might be a wall or like another player or something obstructing us. So we're not always going to move exactly this delta. We might move some fraction or none of it. And we're going to check here and just make sure if we actually moved at all or if there's something like a wall obstructing us. Then we're going to set the velocity equal to the updated component location minus O location divided by time tick. So this is a reverse kinematics. This is just saying V equals dx over dt. And this will make it so that our velocity is equal to like the real velocity kind of. This is just helpful because like if you do something like you run into a wall, then your velocity will reflect that. And yeah, you can try, like, that's just kind of the best explanation for this line. You can try removing it and you'll see that basically the character can like hit a wall but not lose any velocity or something like that. So yeah, so then this right here marks the end of the while loop, you can see. So basically we're going to iterate through this whole loop like several times each frame. And then, you know, ideally, we're going to finish the frame and, you know, this worked out well. And then we want to do some checks afterward to make sure we can still wall run in the next frame. So, again, we're going to do those casts to check where the wall is. And once we get those results, we're going to do some line traces. Oh, yeah, we're going to do some line traces. And we're going to, again, make sure that the player is above a certain minimum height. This time we're going to make sure they're above half of the min height. That way they can like enter at the minimum height but still like fall down a little bit before getting booted off the wall. And we're also just going to make sure that there's still a valid wall. And so if those things are valid, and again, if that velocity is valid above the min wall run speed, or sorry, if any of those are not valid, we're going to set the movement mode to falling. And we don't need to return here because obviously this is already the end of the function, but we will. And, you know, we don't need to start a new physics or anything because the whole delta time has been eaten up already, so there's nothing else to simulate. But this will just set it so that the next frame will be in falling. So now that we're done with the code, we can hop into the editor and check this all out and set up the animations and stuff. Alright, so the first thing we're going to do real quick is we're just going to make that curve float and set up the parameters. So if we go to our character blueprint here, you can see these are my default parameters I made. So you can copy these if you like the video, or you can edit them and tweak them for your game. But importantly here, I put in this wall run gravity scale curve. So we can go to that, we can check that out. That's right here. And here's what it looks like. So pretty simple, just linear curve. You can tweak this to get the parameters you want, to get the characteristic you want. But so I just have a key at -5, -0.5 corresponding to 0.4, and another key at 0.6 corresponding to 0. So this just makes it so that when you're pulling like away from the joystick, away from the wall, or you're not moving the joystick at all, you're going to have some non-zero gravity factor applied to you, which is going to pull you down the wall. But if you're pushing straight along at 1 or near 1, like with the wall, parallel to the wall, you're going to have zero gravity. We are going to need to do some animation stuff. And, like always, I'm not going to go over like all of how I do the animation, like how I actually animate the whole character, because that's just gonna be too much for doing it all on camera. But I'm just gonna like gloss over sort of what I did, because again, like I'm not an animator or anything like that. Like this is very kind of brushwork. The main takeaway was the C++. So regardless though, how I animated it, I always do this is I have this little part over here, this little kind of workbench where I do in editor animations. And well, I don't know why the character looks so funky, but anyway, so basically I use the level sequencer, and I create a level sequence using the engine's little control rig. So here I have this level sequence open, and wow, that character does look very glossy. I don't know what that is. Anyway, so I just make these keyframes. I set this whole thing up, and you can see how I did this in another video. But basically, what the main takeaway I want to show. Sorry, I believe this is in Proning, by the way, where I actually go over how to do this. But so yeah, so the main takeaway I want to show is that okay, I just make this pretty chintzy looking wall run animation, and I put that on loop so that I can just play it over and over again. And then what I did was I made a where is it? It's in animations. I made a mirror table. So this is a new feature in Unreal Engine where you can define all of the mirror types for a bone, and this will allow you to mirror any animations. So then if we go to my animation blueprint, which is just literally just like a copied version of the default animation blueprint, but I just kind of slightly modified it for all my stuff. So I just added a new state in my locomotion state for wall running, and basically I just set like enter the state if we're wall running and exit the state if we're not wall running. And sorry, I should have mentioned that value is set just here. I just grab the character movement component and say is wall running, because I made that function blueprint pure, and we set that, and then we set the wall running is right, which is that other blueprint pure getter we made. So those are two state variables. Sorry if this is going kind of fast, just glossing over this, but so in our locomotion, then we enter wall running if we were wall running, and that just plays this wall run right sequence that we made, but then we feed it through this mirror like node. So we mirror it if we are not wall running right, because this animation makes the character run on the right side, and we just mirror that for the left side. So this is just kind of like a cool little thing I thought would be a good way to show it off in this video. And that's really it. Like you should really be adding, if for like a full-on game, you should be adding way more stuff like IK to place the feet correctly on the wall and get that hand adjusted correctly. But this is just this isn't the point of the video, so this is just for demonstration. So yeah, that's my quick mock-up animation blueprint, and what that ends up looking like is that I can, be running and jump, and there I am moving along the wall. And so, yeah, basically you can see like that's the jump off, so I can run and then I hit space and jump off. And it's funny, it looks honestly way more fluid than I should get credit for, just because of Unreal Engine's nice animation blending stuff. But like you can see, one example of a problem I don't handle is that if the character's wall running very high, their hand kind of is like that. So like that's something you should probably handle in your animation graph if you're really making this a full-on game, or just adding more checks to limit when the player can wall run, like if the hand is in a valid position. Another thing you'll notice that sometimes might feel unintuitive is that you can sort of bonk into the wall and not trigger a wall run because you lose all of your horizontal velocity. So you could change that so that you don't, like you kind of saw it just there. You can change that so you don't get to use horizontal velocity as a condition, but I think it's honestly more accurate. But yeah, so okay, let's do the real test, right? Throw this into multiplayer, listen server and client. Here we got the client on the left side and the server on the right side. So on the client, I'm going to go ahead and run to this wall. I'm going to start wall running, and you can see there it is working. So that's not all though, right? So first, let's just go ahead and look on the server screen, make sure the server can see the client and that looks correct. So if I run here, you can see that animation is playing, and that shouldn't be much of a shock to us. But then also let's make sure that the client can see the server wall running. So the server comes up and wall runs. You can see the client can see that, and you can see that mirroring is working properly. So whether I'm wall running on the left or the right side, the character is getting a valid value even on the proxy. So then let's also start testing ping. So let's go emulation packet lag is equal to, maybe we'll do a ping of 300. So you can see the delay when I move. There's a pretty big delay there. And then let's also turn on show net corrections. And this will mean that whenever we do get a net correction, which is a desync, we'll see that. So I'll show you what that'll look like real quick. So a perfect example of showing a desync is running into a physics box, because it's only simulated on each individual client. So you can see that's what a desync looks like, is I'll get these stutters, and these will show the client being corrected by the server. So in normal movement, you shouldn't get any of those. You can see when I'm just moving around the client, sometimes they'll happen, like, you can see it happen. Oh, I just ran into a box there. But sometimes you can get them just by colliding into stuff, like I got one there. But most of the time you shouldn't get them. They only would happen accidentally from packet loss. So you could say I can enter a wall run, and everything's working fine. We're not getting any desyncs. So this means that in a real multiplayer environment, everything should run buttery smooth. And that's exactly what we want. So yeah, you can see the character doing some different wall runs, and you can see, just the more and more mechanics we build in, the more it just really all comes together, and it really is a cool thing. That was an accent, but yeah, you can see just a cool thing, because we can just kind of work all these mechanics together, and they'll all just sort of flow, and it really does achieve this nice flow of movement, because you can be, entering a wall run, then you can jump off into a mantle, you can slide, you can prone, and the list just keeps getting bigger and bigger, right? So now you can wall run, right? And so I think that truly is one of the things that makes movement awesome in video games, is just combining all of these little features together to make just smooth feeling movement. So yeah, I hope you enjoyed wall running. I hope this works for you, and your wall running looks smooth, and glad you stuck it through the end of the video. Again, like I said, if you had any problems, join the Discord and feel free to comment in there, and I will definitely get back to you at some point and help you out with that. But otherwise, yeah, enjoy.